review because I just started the recording. Here's the force diagrams. This is a side view of the merry-go-round with the axis of rotation right there down the middle. Some of the forces with respect to the x-plane, right, or the parallel to the surface of the merry-go-round, mv squared over r. F sub f is the only force keeping this kid on the merry-go-round, and F sub n equals F sub g. So we move on. The merry-go-round starts from rest, 0 radians per second, and reaches a final angular velocity of 2.5 revolutions per minute in a time of 12 seconds. What is the force applied to the outer rim of the merry-go-round? So what we're saying is kind of like this now. Okay, that drawing did actually come into play. This is like F sub a with r. And that torque is what's causing this thing to accelerate. Because remember, in linear motion, what causes like a box sitting there to accelerate? Force. I mean, who knows what it is? A tension? Is it, magnetic attraction? Is it electric repulsion? Is it, who knows? Force of a spring? Whatever. All we know is that if a box accelerates, there is some net force. So remember, force causes linear acceleration. What causes radial acceleration? I'm sorry, what causes angular acceleration? Torque. Okay? Now, do you see omega initial, omega final time? What can we calculate right here? Acceleration. Alpha is going to equal omega final minus omega initial over t. And then what we have to do here is this has to become radians per second. Okay? Just like you can't do problems with miles per hour. You must do problems in meters per second. So how do I convert this? It's going to be 2.5 times 2 pi, so it's going to be 5 pi over 60. And that's radians per second. Now, how many seconds in a minute? So if we do 5 pi divided by 60, I get 0.262 radians per second. Because it's 2.5 revolutions, right? And how many radians are in a revolution? 2 pi. Does that make sense? Yeah. Okay, no worries. Ask those questions. I love it. Yeah.
Why is FA going up?
Oh, doesn't matter. Could be going anywhere. Does it make sense to you that if I put it here, if I put it here, if I put it here, it's all the same? Right, because all 4 of those spots is going to do what? That's it. I mean, you can't see it, but Eileen was moving her finger like this. Right? All 4 of those spots is going to rotate this. So it doesn't matter where we put it. Actually, I just put it there because that side was blank. Okay? So what do we get for our angular acceleration? It's 0.262 divided by 12. So divided by 12, I get 0.0218 radians per second squared. That is equal to alpha. So we're talking about an alpha. We're talking about torque. What do I use? Torque equals I alpha, right? Oh, and I think Lynn was going to say I is 1/2 mr squared. I think that would have been given to you. Actually, if I give that, well, it is given to you right there. Okay, and then the torque is supplied by what? See, this one is caused by FA, because that's what I'm asking for. So this is going to be FA, R times FA equals 1/2 mr squared times alpha. We already know alpha, so you don't have to crack it open or anything like that. So FA, we can cancel this R right there. We get FA is equal to mr alpha over 2. So the radius is 2 meters. The acceleration we already know, and the mass is 150. And we divide all that by 2, and we get 3.27 newtons. Questions? Yes?
For torque, why do you multiply the radius?
What did I say torque was? Yeah, remember I told you to think of torque as a force that got what? Or a force with a right angle in it. Remember when I said that?
Yes.
Okay, well hopefully you'll remember it now. And do you see how this is a force, but it has a right angle? That's how you want to think of the torque. Because remember, the definition of torque is the distance, the perpendicular distance from the pivot to the applied force. What does that mean? Just, it's a force with a right angle in it. So you go from the center of rotation out to the wherever that force is applied, and then it's got to be perpendicular. Okay, any other questions? Good question, thank you. Anyone else?
FA is force.
I'm sorry?
FA stands for
Yeah, applied force, remember?
applied force.
The one that I told you never to draw in the drawing?
RPM. So RPM, R stands for revolution.
Yeah.
Per minute.
Mhm. Wow, you guys have never heard of RPM?
I've heard of RPM.
How many of you have never heard of the word, have never heard or seen the term RPMs? Wow.
Isn't it in your
When you go home today, I want you to look in your car at the dashboard.
Yeah.
There's two things that go like this. One of them says miles per hour, and the other one says RPM.
Oh, the one that has 1, 2, 3.
Yeah,
Why does it show that?
The thing that goes in.
Why do we
because
really
technically that's the important one.
Yeah.
The speed is just so you don't get a ticket. The RPM is so you don't blow up your engine.
So like, if you get like 2.5 on the freeway.
Yeah, I mean, obviously, if you want your car to be more efficient, drive at lower RPM.
So like under.
That's why you do.
Yeah, that's boring. You can't spin your tires and drift and stuff like that if you're at low RPM. Yes.
So isn't that and your speed directly correlated?
Yeah, well, sort of, because there are gears, and then your gears change the ratio of the wheels to the engine's RPM. So, for example, if you go at 2,000 RPM in first gear, then 2,000 RPM in second, and third, and fourth, and fifth, it's different speeds because the ratio is different. So, for example, in first gear, if you had some sort of military vehicle or some Jeep or something, you might actually get a lower than 1-to-1 ratio, where your engine has to turn several times to turn your wheel once. But then as you go up, then that ratio gets more and more closer to 1. And when you're at 1, it's real fast. All right, I need to finish this. So sorry about those questions. Hold on to them if they're that important to you, because we need to get this, because you guys are taking a test tomorrow. Is this a surprise to anyone?
Kind of.
Really? How's it a surprise? What, let me see. What happened after the last test prep?
Huh? A
A
quiz?
test.
We had a quiz.
Why is it called test prep?
Wait.
Quiz.
Exactly.
We should have another reviewer do all like those
Yeah.
things where you have the multiple choice stuff, dog.
All right. So here, if a child jumps onto the outer edge of the merry-go-round, what is the child's tangential velocity? This is something called conservation of angular momentum. Conservation of angular momentum. If Eileen is cruising down the street on her ultra hipster cool fixie with her like messenger bag and cruising, right? And then I hate fixies, so as she goes by, I drop a bag of rice on the back.
Oh, thanks.
I haven't been on a bike in like 20 years. But so she cruises by, and I take a big bag of rice, like a 50-pound bag of rice. And okay, I'm not gonna kill her. She has a rack, so she has a rack on the back of her bike. Okay, does that make sense?
A little.
She has a carrier device on the back of her bike. So then I drop the big bag of rice on the back of the bike. What will happen to her velocity? Just common sense tells you, well, it's going to slow down, duh, right? Because her mass just shot up by like 60%. Okay, so do you see that the same thing is true here? When the merry-go-round's going around, if you stand there and you wait and you jump on it, it's going to slow down. And this is just conservation of momentum. So when this child jumps onto the outer edge, we're going to assume that the child jumps not tangentially, but radially. So the child jumps on straight towards the center. Because if the child jumps parallel or tangential, he'll speed it up. Right? Does that make sense? Because how do you speed up a merry-go-round? You go tangential, right? Like this. So if you jump on that way, you'll speed it up. So how do we get this kid to jump up? So the kid jumps on and grabs. Okay. So that means initially the only momentum is from the merry-go-round. Now we have the new momentum of the merry-go-round plus the momentum, the kid's final momentum. And this is angular momentum. Momentum is what? P equals mv. So what is angular momentum? L equals? What? There you go, I, because m is like I, and v is like omega. So L is I omega. So we have I of the merry-go-round times omega initial equals I of the merry-go-round times omega final plus I of the kid times omega final. Hopefully everybody's okay with the fact that the kid and the merry-go-round have the same final angular velocity. Because the kid's not moving, just grabs on. Okay, now, did we find the kid's velocity?
Tangential velocity.
Oh, we found that. Did we find the tangential velocity?
What's a child's tangential velocity?
Oh, what is the child's? Okay. Oh, okay. So what was the merry-go-round already moving? Yeah, because we already applied it. So what was the initial angular velocity of the merry-go-round?
2.5.
So what did I convert that? 262 radians per second, right? That's omega 0. 0.262 radians per second. That was the original. Because we need that, right? So then, what is the child's tangential velocity? And then the other thing we need to remember is that omega is v over r. So v is omega times r.
Wait, 0.262 is final? Omega?
Was that final?
Yeah.
Oh, I'm sorry. I didn't want the well. Okay. Oh, what we're assuming is that if somebody pushes this thing and gets this thing moving, and now it's spinning, then the kid jumps on. So that's why the 0.262 is after part B. So now it's spinning at 0.262 radians per second. Yeah, that's the initial. So we are right. That's the initial. Now the kid's going to jump on. And when we find the final angular velocity, all we have to do is multiply it by r, and we'll get v. Right? So v is equal to omega times r. So if I look here, look what I get. I get omega final is equal to merry-go-round's initial moment of inertia times omega initial over Im plus Ik.
Wait, what did you want it in radians and not in?
I put this in radians per second.
When the y is in v omega r.
Oh, well, this is just conversion. Remember this definition? Because what are they asking? They ask for tangential velocity, not for omega. They ask for tangential velocity. They ask for VT. This. They didn't ask for omega. But everything we have is in omega right now. So how do we get from omega to V? It's through R. Remember that? Theta was X over R. Omega was V over R. Alpha was A over R. Okay, and so at this point, then all I have to do is say V is going to be equal to Im omega initial over Im plus Ik times R. And that will give me my final answer. So if I plug all this crapulous stuff in, then I get 1/2 m r squared omega initial over 1/2 m r squared plus m of the kid r squared times r.
What happened to the second omega final?
Oh, I factored it out. See that? See, like here, omega final times Im plus Ik. See, and then I just solved, I divided Im omega I by that. What's the matter?
Hey, what does that say?
This?
Yeah.
Yeah, that's supposed to be omega.
And then underneath.
Yeah, it went, I think it spazzed right when I was trying to do that.
Underneath is just INIK.
What's that?
And the denominator?
Yeah, it's Im and Ik.
Um,
I of the merry-go-round plus I of the kid.
so that V equals omega R, but like omega, you plugged in omega F. Why?
Well, V just equals omega R, whatever omega you want.
Whichever one.
Yeah. So for example, if this initial velocity is this, if I want to know the tangential velocity of the merry-go-round, because remember the kid hasn't jumped on yet. If I want to compare the merry-go-round, I can just take this and multiply by the radius, and I'll get the meters per second of like an ant sitting on the outside of the merry-go-round. Now, if the kid had already been on the merry-go-round in part B, and this was the final angular velocity, then this answer would be stupidly simple. Because all I would do is take this, multiply by R, and I get my answer. But because the kid jumped on after it was already going that speed, then we get all this jump. Yes?
How come for the I for the kid is MKR squared?
Yeah, okay, so if we look at, does it make sense to you that a disk spinning like a merry-go-round, its moment of inertia is weird because you can't say exactly where's R. Now you think like, well, wait a minute, R is just to the outside edge. But remember, moment of inertia is the sum of the masses times the distance to the center of the rotation. But where is the mass of a merry-go-round? It's all over the place. See, what R do you use? Do I use an R that's 1 centimeter from the center? Do I use an R that's 1 meter from the center? Do you get what I'm saying? But if I take a mass like this and spin it, can you tell me R clearly and unequivocally? Yeah, it's the length of the string. Because this is a single object. And so its mass, when it moves in a circle, the moment of inertia is just mr squared. So can you imagine that this yo-yo is the kid on the merry-go-round? Right? Because he's just a body rotating around a central point. But the merry-go-round, its moment of inertia is more complicated because its mass is distributed through the whole object. So that's why we have to use I as 1/2 mr squared.
How come there's no 1/2 on the kid?
Okay.
Okay. Okay, how do I say this differently? She asked, how come there's no 1/2 on the kid?
I don't get it either.
So 1/2 of the kid?
Okay, well, clearly what I just said didn't make any sense because nobody got it either. Okay, let's start with this. Is everybody here okay with the fact that this moment of inertia for the blue yo-yo is mr squared? Is there anybody who's unclear on that? Please say so if you're not.
I am unclear.
Okay, the definition of moment of inertia is mr squared. So if I tell you that this yo-yo has a mass of m and this string is r, then you should be like, okay, I may not know everything about what moment of inertia is, but I know that for that yo-yo, it's mr squared. Now remember, moment of inertia is like mass. It's your resistance to angular acceleration. Okay, do you remember when I raced the disk and the hollow tube
Yeah.
down the incline? Which one won? Yeah, the disk, because there was mass at the center of the disk. But the hollow tube, all of the mass was on the outside. So the hollow tube had a higher moment of inertia. So when you calculate moment of inertia, you have to use calculus. And when you use it, you're basically trying to say, you're trying to add up all the moments of inertia of every particle in that object. And if the particles are more in the center, then that object has a lower moment of inertia. Okay, it's simply, so what you have to do is know that I will give you the moment of inertia for anything that is not like this. If something is moving like this, I expect you to know that its moment of inertia is mr squared. But if something is like a disk, if something is like a sphere, if something is like a rod that's spinning, I'll give you that. So moment of inertia is your object's resistance to rotation. Okay, and so you just have to like know that for a single object moving in circular motion, it's mr squared. But for an object that's rotating about itself, you just have to use the whatever it is on page 254. Because I don't know if it's not helpful if I do the calculus. Yeah, so I don't know. The question is, why is it half? So here, this is the moment of inertia of the merry-go-round. Do you see the merry-go-round is a flat disk? That's why it's 1/2 mr squared. This is the moment of inertia of the kid. And the kid is a single object rotating around the center of the merry-go-round. That's why it's mr squared. But they're different m's, right? This is the mass of the merry-go-round, this is the mass of the kid. Shauna, does that make more sense? It's like if there was a car and a person, and you applied acceleration to both, right? Or whatever. Like you don't worry about their masses being different, right? It's like the car's bigger, so it has more mass. The person's smaller, so it has less mass. Does that make sense? Okay, so an object, objects have different masses. The same thing is true about moments of inertia. Objects have different moments of inertia. And the moment of inertia of a disk is 1/2 mr squared. The moment of inertia of the kid is mr squared. It's simply a function of their shape. Okay, well, anyways, let's move on. So now you can plug everything in and get an answer. Oh, look, can I cancel all these r squareds? And then, I don't know, make my life easy, I'll do that, put a 2 there. So then the mass is 150 times omega, which is 0.262, divided by the mass, which is 150, plus 2 times the kid. How much is a kid? 35, so it's 2 times 35. And then multiply that by r, which was what, 1.5? What was r? 2, okay. And I get 0.357 meters per second. And that should make sense, because if I look at this right here, if I multiply this by 2, I get 0.524 meters per second. So did the kid slow the merry-go-round down? Yeah, and does that make sense to us? Yes, that's reasonable. Because this is omega, so to get v, you multiply omega by a radius.
But I'm still confused on why, I understand up to I m omega m equals I m.
This right here?
Yeah, I understand up to there, but then
You're good up to this point, or you don't get this point?
I get that.
Okay.
But I
And
get
after it's algebra then.
so do you convert omega? Yeah.
Yeah, I convert omega final to v, basically like, okay, see, this is omega final, right? This part? So I insert this into that equation. See, this is v equals omega r. Right, can you see it? It's v equals omega r.
Because it's tangent.
Yeah, and this is omega. So all I did below the one where you said you can understand, everything I did after that was algebra. Based on what I already had up here.
What is that 0.524 thing?
That is the original tangential velocity of the merry-go-round. This is the tangential velocity after the kid jumps on. And I was just showing you that it does make sense. Because we predicted that it would slow down, and it did.
Wait, how did you get that though?
I just took omega times r.
Okay.
So you isolated
Yep.
omega.
But that was no part of the problem. I was just
That's no part of the problem. This is not part of the problem. Well, technically this is part of the problem, but I wanted to show you, so. But this is not part of the problem. You don't need that for any reason. Okay, yes?
for the third line, did you just back out the omega?
Yeah. See, like I took this right here, and I just factored out the omega to get this.
But it's still set equal to the...
And then I solved for omega final. So that's this over that.
Oh, so that's still set equal.
Yeah, these are all equal. Sorry, your math teacher would have a seizure if they saw multiple equals on the same line. Okay, questions? All right, so what's the concept here? The concept is that momentum is conserved. All right. The other concept is angular momentum is I omega. Okay, and then finally the definition of I we have to remember. You do not have to memorize the formula. You have to remember that moment of inertia is based on how your mass is spread out. If you are a single ball or person or object going in a circle, then your moment of inertia is just mr squared. If you are an object that's rotating, now your moment of inertia is some weird thing that I should give you. You will never have to come up with that on your own. Okay? All right, now, if the Merger-Arm was moving that, counterclockwise and child started running clockwise, what happens in 10 seconds? What is the angular? Forget it.
Awesome.
Yeah, that one's too hard.
Wait, what was the answer?
It goes fast.
That? I don't know. If you want me to do it, I can do it.
I'm gonna do